Okay, so let me get us started. 11:32. I guess we can wait a minute or so. Remind me when you got your PhD.
In Bengal University.
But when?
Oh, a year ago. Like,
A year ago?
No, 2 years ago. So 2021.
Wow, it's so fresh out of here. Yeah. Okay. Well, I guess we can get us started. It's my pleasure to introduce Dr. David Benisty, who is visiting us from the University of Cambridge. And you're officially at Department of Applied Mathematics, is the DAMT, which is where famously Hawking was from, and they're famous, I guess, astrophysicists. So David is a postdoc there, working on modified gravity, but he recently, as you just heard, has finished his PhD at Israel, at Ben Gurion. He's an academic grandchild of Benisty, who some of you may know, Jacob Benisty, who invented the entropy of black holes. But today he's going to tell us about dark energy and how you can test it with two-body problem. And he's happy to answer questions in the middle. So if you have questions in the middle, just please feel free to interrupt.
Yes. So thank you very much for the nice introduction, and it's really good pleasure to be here. Ask me many questions as you want. Again, it's going to be like a bit like diverse because it's like in one side theoretical work, on the other side it's like a bit observational. So I will try like to do it like more in the simple terms, so like to give more motivations and this sort of stuff. So this is like an overview for what I've done, but let's go like to bottom of line. Why do we need like dark energy? So I'm gonna like to give you like a short overview for certain measurements that I think that most of the people here know, and why do we need like to add Einstein cosmological constant inside to R term. So I mean, it's like a different data set that we have from cosmology, especially from cosmology. And in order actually to explain the expansion rate of the universe or the cosmic microwave background shape itself, we have to add the cosmological constant inside. Okay, so I mean, for instance, like you see in the upper plot, here this is like distance modulo versus like in different redshift. Now, as you can see, if you change the omega mater and the omega lambda, you get like different expansion rates. Okay, so really, in order to explain why the expansion rate is have like these values currently, you have to add the Einstein cosmological constant inside your equations. Okay, at least one modification inside. And there are like many others, I mean, from Barton constellation and from the CNB that, again, like to explain exactly this shape, you have to add lambda inside. Okay, many others. So now it could be like different other motivations for why do we need modified gravity. So I mean, in my terminology, even lambda is like modified gravity because you need to modify R. Obviously, the Einstein was predicting lambda, but I mean, even like in that sense, I could call this like modified gravity. So I mean, there are like other motivations that related maybe to inflation, like the expansion rate before the Big Bang itself, that you need like to have certain modifications, or to explain other phenomena, why the cosmological constant has like its value, or other like motivations. But bottom of line, the still open question is like, is this really Einstein cosmological constant? I mean, like the minimum modification that you have to add, lambda, is it really the only modification, or this is part of a bigger theory? Okay, so let's say my own motivation, like to introduce like this question to answer. Okay, maybe the bottom of line theory is going to be R plus lambda, but I want like to really see it in other system, or to test it like in other system. So like the minimalistic extension, or a simple extension to Einstein cosmological constant that we see here, this is like the R Einstein theory, and this is like the cosmological constant. It could be what's called the quintessence model, okay, which is like very famous and familiar, most of the people last night, I guess. So it means that you can restate Einstein cosmological constant by a scalar field. Okay, so now it's
Sorry. Someone is not muted.
So it means that now instead of like having really boring constant in some sense, you can have like a dynamical field, okay, that behaves approximately as a cosmological constant in certain conditions. So what are the certain conditions, for instance? So if you are taking like the Einstein, if you are taking like the quintessence model, so it gives us like a kinetic term. This is like, it comes from the kinetic term itself, phi dot square, and give us some potential, okay? Now, as you can see, like the first equation is like the density, and the second equation is the pressure of cosmology. Now, if we were taking like the limit that the kinetic term is going to be partially negligible to the potential, it's what's called the slow roll approximation. So we recover the Einstein cosmological constant. Okay, so this is like the simplest extension. But here, the field is become like dynamical one. So it's going to be like more interesting, or to describe like more different phenomena. But again, the idea is like to show that we can extend lambda to another families of theories. Any questions? But we have like certain limitations which theories are still viable or they are not viable. Yes, okay. So there was like certain event like a few years ago, but it had like a strong statement for modified gravity. So they measure, I mean, like in that date, they measure also like the neutron star emergence. So they measure also like the gravitational waves emission, but also the gamma ray burst, the light that comes from this emission. Okay. And because they able also like to detect the light and also like to detect the gravitational waves, they could see what is going to be the speed of light, and also what is going to be the speed of gravity. I mean, like the speed of gravity means the speed of the propagation of gravitational waves. Okay. And what they found that they are the same. Okay, up to 10 to the power of minus, really small value. Okay. Now, what is the problem? So some years ago, like about the 70s, a certain painter, now he's a painter, but he's like a very famous physicist, condition physicist. It's called Benisty. He tried like to introduce the general combination between scalar field that I showed you like a second before, but the general combination between phi and Einstein term R. Okay, so he introduced what's called the Benisty theories. So you have like the scalar field and also like the kinetic term, the X, but then like he introduced like all the possibilities. Now, for certain permutations of this combination of theories, they found that the speed of gravity and speed of light are not equivalent anymore. Okay, how so? I mean, you can imagine this, that if I'm taking like the Einstein term and I'm like perturbing it over like a flat space-time, I'm going to get a wave equation. But if I'm going to introduce some scalar field or some other component, I could get a friction-like terms, okay, inside my wave equation. And then this is like perturb the behavior of the gravitational waves. Okay, so there is actually like much more extensive parts here, but all of these parts are no longer possible because of this constraint. Okay, so we have really to take care also like from this constraint on modified gravity. And these are like the theories which are still viable, and this is like publishing physical review letters one day after they published. It was uploaded to the archive one day after, like, okay, speed of gravity is speed of light the same. Now let's put what are the theories which are correct. Any questions so far? Yeah, so I mean, these terms, these are like the general functions, right? But I mean, if you perturb these like functions, you can see that speed of light is like changing. I mean, if you have like other,
but these ones don't change. Like these ones
don't change. That's correct. Yes. Okay. Because there are like other parts that I wanted like to cut because it was looking too ugly. Sorry, but
general function for
yes, exactly. Because I mean, you can also see that here they are not coupled to R or coupled to other higher terms of R. They're only like as a matter field. right? I mean, you have like R and you have like all the matter, but it doesn't like change the wave equation. Like it's like the motivation theory. It's only like a source, these two parts. Okay, other parts are like Einstein tensor itself inside the action. So this is why you get like friction like terms or something like really crazy.
So, for students here, Benisty was a student here, right?
That's the most important I was gonna say. He was a Waterloo
I
student.
didn't know that.
Yes.
So, okay.
And then he was a full professor here. Yeah, just reading Wikipedia. Between 79 and 81.
Those were times it was easier to become
So just letting you know, this is like become really one from the theoreticians like in cosmology. So I mean, you have like a really good chance for that. I mean, good for you. Okay, so yeah, please.
They make this calculation. Because the template, calculate the gravitational wave, all of those are based on PR. Is that we assume, okay, the wave it started from there on, behaves the same as the wave, not the only thing that matters.
I mean, I'm not entirely certain. I mean, yeah, I see what you are saying that like the simulation, they're like, but I think it's really related to measurement, direct measurement, like the light and also like the gravitational waves. So I think it's not like in addition to some simulation. So it's like a direct measurement.
A strong field limit on your field model.
Low.
Have to be on.
Oh yeah, yes. I mean, you call the GR if you have like all of the functions to be one.
No. I mean, on the strong curvature.
If it gets close to the black hole and the beam down,
Oh, I see now what you mean. It depends on the function. I mean, here this is like a general. I mean, so you can have like any different behavior. But like, let's say like on the other direction, you could solve, maybe some people do, solve the black hole solution in the Benisty and then like to get all of these things. But it's like a really general function that could behave in what way you want. So I mean, here it's like, okay, let's introduce like the general functions, but because I have like this constraint, all of the other parts are like things.
I think Chazon's question is whether this constraint is reliable, because if you modify gravity, then you change the waveform. But I think one thing about this event is that you don't actually even see the strong gravity. Just see when things are far apart. So it's sort of like Newtonian gravity. Yeah.
Any more questions? Yeah.
Very caveat with that.
Sorry, I don't hear.
The frequency dependent measurement.
Okay.
And the pressure relation could have a more complicated K dependence if you have those more complicated functions. So
That's,
in an EFT point of view, you could have.
yes, and there are like several papers by I think Amendola published this a bit after like how to recover some theories. So they are going to have like still like a speed of gravity which is not like the same, but then on the certain conditions like recovery. So it is still a possibility. But I think in some sense because the constraint is really strong, the possibilities that are not like that big. Okay. So now my main motivation for the modified gravity theories that I will introduce in a second is actually, okay, let's go to another systems. Okay. In order like to take like these viable theories or some certain theories that I will introduce and try like to using like the motion of stars, I mean in future gas, this sort of stuff, test alternative theories of gravity. But before I'm going to do that, I'm going only like to introduce like a term. You don't have to follow the whole equations, but I mean, bottom line, it's only like to show you that this is possible even like to solve analytically besides numerical solutions. It is possible like to find analytical solution for two-body problem, for the two-body problem. Now, this one you can introduce by what's called the mean anomaly. Okay, so in the mean anomaly, you are trying like to introduce another angle that surrounds like your system. So this is like the true anomaly, the true angle, but you introduce it like a new one, which is like the mean motion. Okay, now when you're taking like this sort of like angle and you parameterize R, I mean, you can see here, A is the semi-major axis. If somebody is not familiar with the term, tell me immediately.
I thought this would be undergrads, because you 75 last term. Right? Very one of my students.
So it's like that. You know what is mean anomaly? Yeah.
I wasn't in his class.
Professors, we need a reminder.
So, I mean, you introduce, I mean, like, this is the solution of two-body problem for the Keplerian problem. If you have like Newtonian force, this is the solution. R versus the true anomaly, the true angle.
By the way, I should warn that we do have some people online and they don't see your ruler.
Okay, I'll
So,
try to
no,
use
but
like my,
I think you don't have to use that, but you just, maybe if you just say in words, like you're looking
Yes.
at the top and the bottom.
I think,
No, but do you use the ruler? No,
Okay.
Yeah. I can do that. How about
okay,
that?
okay.
I will
Thank
do
you.
that.
So yeah, I mean, this is like the analytical solution for a two-body problem. I mean, so if you know like the Keplerian head and the Newtonian force, this is the solution that you get immediately. And phi is the true anomaly. So this is like the angle that sits like around around the sun. Okay. However, you can introduce another angle, which is like over the mean motion. Okay. And you parameterize this angle by this term. R equals to A minus this cosine. Now, why this is like cosine makes sense? I mean, because cosine can run from -1 to 1, right? So you're going to have A plus minus E. Okay, that makes sense. This is like the radius is like in elliptical motion. But bottom of line, when you take like this analytical solution or this parameterization of R, and you introduce it like in the energy equation, the two-body problem, you get the second equation, which is analytical term. But what you see here, you connect the time to the mean motion, to the angle. Okay, so you have like two equations that describe fully what is going to be the analytical behavior versus time, not versus the angle like here. Is it clear? I mean, if I have like the time, I can find the angle, and from finding the angle, I can find R. So this is like analytical solution that describes the full problem versus time.
Does eta have a constant angular velocity? Is that what you're saying?
It's like surrounds the whole motion. And you can connect phi to eta by the second term. But you can imagine that you're like surrounds, I mean, the true motion is like over the elliptical one, but you can surround it by some circular motion. Okay, if you can imagine this.
Eta is your thing that's right.
Yeah,
You.
eta is you. Okay, my mistake. Okay, but bottom of line, this is like analytical, beautiful solution. And why I'm mentioning this? Because Tabito Damour originally found that using the same parameterization, you can find analytical solution also for GR. So the first post-Newtonian, in 1 second, I will introduce that. You can actually see that you have also like analytical solution for GR problem, two-body problem. This is why it's like so important parameterization. Any questions so far? Okay, so let's go to the next. So, okay,
Is that too much?
so what I would like to show you bottom of line, I mean, leave out like, you know, this is like creepy action, but bottom of line, because you know the analytical solution for the Keplerian problem, the Newtonian potential, if you have the first order correction from general relativity, you can find also analytical solutions. Okay, so as you can see here, these are like the differential equations, R dot and theta dot, when you introduce like some additional GR terms. Okay, that's all. This is what I would like to say, not something beyond. Let's go next. Oh, yeah. And what you see here, these are like the analytical solution that Damour found. or GR. So what got changed right now? You define a new eccentricity. So the eccentricity that you have seen before is only multiplying by some term. This is like the analytical solution that we've seen like in Newtonian. Okay, but now ET is only multiplying by some factor, as you can see here. So if you have only like these two equations and you run like a computer simulation, you can actually get the precision that you see from GR. Okay, but what I'm trying to say, you can have analytical solutions for two-body problem, even for general relativity, and therefore also for modified gravity. This is what I'm trying to say. And you only perturb the analytical solution that you have from the Keplerian problem. Okay, any questions? Okay, well, let's go further. I think we can drop this. I found like some analytical solution for Yukawa potential that's not related to this topic. So the theories that I was interested like with my host Ann Davis, she was like testing what's called the chameleon type dark energy. So I mean, in this type of theories, the scalar field that you introduce that can replace the cosmological constant is now coupled to matter. Okay, so it has like some coupling to matter, and then like it has like some additional interaction. So what is like the idea? The idea that maybe the cosmological constant itself is not like what's called minimally coupled, that you have like lambda plus some other fields. But now that the matter and the cosmological constant has like some interaction inside. This is like a general framework. Any questions? What I want actually to show that if we introduce this sort of interactions, is going to affect the two-body problem. It's going to introduce a new precession. And this is why we can actually use like data and then like to constrain like this interaction to see if dark energy has some interaction with matter or it does not have. Okay. So these are like the two possible interactions. I mean, we have what's called the conformal. This is with the scalar potential itself, or this formal. It means that the kinetic term is coupled to matter. So in order to couple the kinetic term, we call this like this formal, or the order to couple the scalar potential, and we call this conformal. That's all. If beta goes to 0 or lambda goes to infinity, we recover GR, recover general relativity.
Here you want to say this is a different metric, right?
Yes, it's going to be bar. This is the bar. Any questions? This is like a bit mathematical, I know, but I'm trying like to give more the intuition. If this, any questions so far? Okay, so I think let's go like to the solutions. And in this original paper by Ann Davis and Philip Braggs, they like solve like these general theories like in two-body problem. But what you can see, and this is like what interesting, the punch bottom of line, that you see the conformal interaction and the disformal interaction inside the action itself. If you take beta again to 0 and lambda goes to infinity, you recover the Einstein-Born-Infeld-Lagrangian or the two-body problem. So the interactions themselves, they are now introduced in the action. Okay, this is what I'm trying to say. Now, I solved this like also numerically, and here what you can see, this is like certain orbit, or we introduce like in a second what is this orbit. But in the blue line, this is like for general relativity, the regular precession. If I introduce like the conformal interaction, it introduced a new precession, like higher precession. And if I introduce also like the disformal interaction, it trips out the whole simulation and the precessions become really much bigger. Okay? But bottom of line, what I'm trying to say, if dark energy, if the cosmological constant has some interaction with matter, or the conformal or the disformal, it changes the whole motion of two bodies. Okay, is this clear? I mean, is this the idea here clear? Okay. So, I mean, here this is like the analytical solution that we found. So I'm not going like into that direction. But I mean, again, it's like to state that if you take like this beta and lambda goes to 0, you recover GR. But now we found like a very interesting phenomenon that related to these interactions. We found that, for instance, like in the precession term, I mean, the precession term that you see here, this is for GR. This part is like GR. And this is like the modifications. Okay? This one is like the non-GR precession. We found that there is like a dimensionless parameter that always appears in the equation of motion. What was the dimensionless parameter? Is the period omega, the period of the motion, over the disformal coupling. So it means that if I want like to test this disformal interaction, I have to go to a really high frequencies. Okay, if I'm going to have like systems like the solar system or pulsars, they have like higher frequencies. I could test lambda, this formal interaction better. Okay, so now let's go. So the first system that I tried like to introduce, it actually was like a paper. Please.
Those are analytical primitive solutions.
Yes.
What are the expansion parameters?
G-Newton, yes.
That's it.
C, 1 over C squared. It's what's called the post-Newtonian. Yes. Okay.
Not about the chameleon part.
The chameleon interactions, I mean, like beta and lambda, they appear in the parameterization that you put for the functions. So this is like beta and lambda. Yes. Okay.
Is there any assumption about
Um,
there be small coupling?
yeah, the beta should be small and lambda should be like very large because it's 1 over lambda. Okay. Yeah. So one interesting system that I used to constrain like this interaction, it was like the galactic center. So in the galactic center, we know that it's obviously like a black hole, Sagittarius A, but we have also like very detailed knowledge about the locations of the star around the black hole. It's called the S stars. Now, from 1990, the gravity collaboration and also like other collaborations, they, they took like any year a measurement of these stars, a picture, and they found like the location. So from 1990, we have like a detailed motion of the S2 and other stars. Okay, so this is like the projection of the sky, the X and the Y, and these are like the velocities. Okay, and this is like the full precession of the S2 star that you get for more than 20 years of measurements. So we have like the location, we have the equation of motion from modified gravity, and then we can introduce Monte Carlo simulation to constrain like this, these theories. So in this paper, I found like the constraint of the conformal and the disformal coupling. Okay, so if I use like the S2 star and another star that's called S38, and again, it's like we have like a full detail of the motion and this sort of stuff. And I got like the constraint on beta square is going to be like 10 to the power of -3. Beta, to give you like more intuition, it's like how much the Newtonian constant is going to deviate. Okay, so it's like up to 10 to the power of -3. And the lambda is about 0.1 mega electron volt, which is pretty strong. Yeah, because like in other measurements, they are much, much lower. So here you can select the best fit that I try like to use for GR versus the conformal and the disformal interactions. Okay? So obviously for more years, the constraints are going to be much smaller. Okay? Any questions so far?
Sorry, so in your table, you have the constraints for those.
Yeah, okay. So Cassini is like introduced some constraint on beta because he measured like the light reflected from Saturn rings. So he found like a constraint of 2 10 to the power of -5. So I added like as additional constraint. If you have like also like Cassini in addition, so the constraint on lambda is going to be better. Okay.
So yeah, for your lambda, the constraints get worse.
No, I mean, so the bound on lambda is going to be tighter.
It's not tighter, it looks like it gets bigger.
Oh, no, I think you're right.
Why does it get bigger?
Because it gets bigger because now you introduce like to have like some sort of like a delta function inside. So you have like more freedom for the precession. like to play role inside it.
That doesn't make. It should get smaller because you're adding more constraints. So there's something, I mean, unless it's very non-Gaussian.
You think that you have like something like prior volume effect?
Yes.
Can you show it here in this
Yeah,
plot?
here this is like, yeah. I mean, you can see plus Cassini, this is like become like a delta function inside.
Uh-huh.
So this is like a tighter in some sense. I mean, so it could be have like,
But the error in lambda should become smaller if you put.
no, but in Cassini, it's only give you like constraint on beta, not on lambda.
You're using the other one at the same time,
Yes,
right?
yes. Yeah.
There's something funny.
Something, okay, I need to solve it. Okay.
Does the marginalizing does that?
Imagine they should do the other. I guess you're saying the red is with the without the Cassini,
Without the Cassini, yes.
and then with the green, then the blue is with the Cassini.
No, the blue, yes.
Somehow it actually shifts. So there's something very non-Gaussian.
Mhm.
Yeah.
Yes. No, that's a very good question.
Yeah.
I need to think about it. Yeah.
It might be the prior stuff. Okay.
Yeah, maybe the prior. Okay.
I remember there were this constraint from one basis.
Oh, yes. This is like a paper that we're working on right now, because this is like the lens steering effect. So we calculated like the lens steering and then like laser, the Gauss, all of this like system, they measuring like the precession if you have like a gyroscope. Ginger. So this is like a different family. So,
They had already fixed some down. Okay, right now.
in beta, yes. In beta, there are some. The best one is Cassini.
Cassini doesn't constrain lambda.
No. Because like the effective, if you write it now like the effective metric, you get like off diagonal terms. And if you have like a light, so you're going to have only like impact of the
Diagonal.
diagonal.
Okay.
Right.
I have a question.
I think I'm just not understanding what you're saying about the frequencies. You're saying that S constraints on lambda are coming from high frequencies.
Right.
Compared to S stars, like period.
Yeah. This is why pulsar they're going to be better. That's correct. So exactly for your questions. So I mean, this is why actually we also like choose pulsars. Okay. So I mean, what is the idea beyond pulsar? I'm going like to end like about like this system. So the idea about binary pulsar, it was measured like originally in 1975, and up to today we have like plenty of measurements, plenty of events. So the idea is like that you have like a pulsar, like a star, that has like a strong magnetic field, okay, that give you like pulses to Earth all the time. And from measuring like the time of arrival of these pulses all the time, you can get what is going to be the period changing or the precession, the periastral advance, and all of these sort of like parameters that relate back to the two bodies. So if you have like a pulsar and another pulsar or another dwarf star. Okay. So we use like these like systems. Yeah. I think there is like one book I want to introduce before. Okay, so here. So as you can see here, this is like a different systems. Like this is like the potential, the Newtonian potential. So for Earth or Mercury or this two star, which is like on a strong gravity regime. But here you can say like the pulsars. Okay. So obviously the period is much higher. So this means why the constraints on lambda are going to be like the best. Okay. So here this is like the precession. Here this is like the period changing. Okay, some parameters that you measure from the events. Now, there are two interesting events of pulsars. Please. Yeah. Why is the Newtonian potential?
Where, like the potential at the surface of the star?
No, of the system. squared. So GM over A C squared. A is like the semi-major axis, and M is like the total mass. The rough estimation like of the system.
For the two-body problem, right?
Oh, yeah, right. Why is that the relevant potential instead of like a surface? Right, I mean,
What do you mean like this?
well, these neutron stars, you know, at the surface, they're like almost relativist.
The masses in the neutron stars about solar masses. And the semi-major axis they are bit closer.
Yeah, I understand that the semi-major axis is large enough that the, you know, that the orbital motion is not.
Right.
Right. But for these chameleon or Einstein theories, I thought that what matters, you know, is potential where the matter is.
Oh, now I see what you're. This is like in particular for these solutions. So you try like to solve like for chameleon or what is like the spherical symmetric solution. Here it's like to say I'm trying like to guess that I have like a general coupling, but then I know that it's going like to affect on the two-body problem. So it's not like for the spherical symmetric solution, it's like how this like impact in two bodies, like a different solution.
But just to be clear, so you're not assuming there's a screening happening here.
No.
So there's not in the screening regime, but I mean, I think you're, I mean, it depends on the,
Because there were chameleon, so I thought that we were like,
It's chameleon type theories. I mean, but I mean there that you have like a general coupling between the matter fields and the scalar field. This is like the chameleon, right? I mean, this is like the idea.
but the premise I thought, you know, of the chameleon theory, you know, is that in the strong gravity,
Right.
they go back to G-bar.
In the strong gravity regime, you go back to GR. Yeah, that's correct. But I mean, now
So then are these neutron stars on the
no, okay, so I mean, here we introduced like a general format. It's not like necessarily like certain chameleon type theories. So we have like the conformal and the disformal interaction. Okay, and for these ones, this is like the general two-body problem. Okay.
Is it gonna happen?
can you,
Or you have to add additional?
If beta goes to 0 and lambda goes to infinity, it's like it goes to GR. Okay. I mean, like in these theories, they're trying like to say, yeah, maybe like the dark energy is like changing from a different energy density. Right? I mean, this is like a chameleon, right? I mean, if you like different raw, you get like different dark energy value. And then like in the solar system or something like that, you can screen this out. Right? But I mean, here it's like to say, I'm taking like the general couplings between scalar and the matter, and then using that two-body problem.
but you also assume it's massless.
Yes.
So that's the key thing, because chameleon is massive and mass
Oh.
gets very big. But here you assume it's massless. So I think that's, yeah.
Okay, thank you.
So it's not really chameleon, but it's, I guess chameleon is.
Motivated by
Chameleon is,
Yes.
yeah, but it's not the same.
Yes, okay, thank you. Thank you. Okay, so just wanted like to show, this is like the measurements. I mean, you can see like the period and the precession, but why I want to show like numbers, I mean, you can see that the errors are really, really low. And 10 to the power of minus 5, 7, whatever. I mean, so especially the double pulsar, but also like the whole stellar pulsar, because this is like detailed for many years, we have like very high precision. So anything that related to the two-body problem is actually like the best theory like to test, okay, or the best system to test.
Sorry, okay, sorry.
Yeah.
So I'm just sort of puzzled about like one of these. So, okay, like, so I thought that you were studying these models, you know, to solve the dark energy problem. But you're assuming massless with no screening mechanism, right? So then are the strengths imposed on these parameters so strong that you cannot then solve the dark energy problem?
Not solving the dark energy problem is like to state if there is like some hidden interaction of dark energy. Otherwise, it could be like, okay, dark energy, but then it's like the cosmological constant is like still weird. Right? Why it has like this value and this sort of stuff.
If according to high gravity theories with no screening mechanisms, are you making dark energy any less weird? They talk about
No, but I mean, no, that's fair enough. But then the question if this is like, there is some hidden interaction or not. So what I'm claiming, I could tell you that if there is like some additional interaction, it should change the two-body problem. Then like the constraints are going to be strong. So, okay, so let's go like to, so the idea like of using like pulsar to test modified gravity, this is like very general thing. So you can see like the different measurements of the period changing or the precession or other what's called the post-Keplerian parameters. This is like related to the time of arrival. So they don't give you directly the value of the mass. I mean, if you can see here, right? I mean, you can see that there is a relationship between the measurement, the omega dot, and the masses. But you cannot know directly from the measurement what is going to be the mass. However, if you're taking like the full contour of all of these parameters together, they are falling like on the same point. And then like you can say, okay, this is the mass of the pulsar and the companion. Now, there are certain theories that are going to give you like different contours. They are not like falling on each other. So this is why it's like ruling out these theories. Okay? Or giving like a very strong bound on the possible theories. So, I mean, here, this is what we use like to constrain beta and lambda. And then you can see, this is like the Cassini bound 10 to the power of -5. And from the double pulsar, we got like almost the same constraint, 10 to the power of -5 as well. And the bound on lambda is about like 1 mega electron volt, which is very tight. Okay. And
You have title at 0.06 mega electron. And actually title is the bigger one for lambda,
Yes.
right? I see. So 0.5 is
yes,
confusing because one should be big, the other should be a small. So
Yes.
I think you should have inverted your bars there.
yeah, okay.
Mhm.
So, okay, I don't have like time more. Let's see about the local group, but so bottom of line, what we would like to say that we can generalize the dark energy interactions into like these couplings. Then from mean, which normally we can actually find analytical solution for the problem, but also like numerical solutions. And with using all the galactic center of the pulsar timing, we can get like a very strong constraints on these couplings. So I mean, here you can see like a comparison between Mercury or the S2 precession, but here this is like the constraint from pulsars. Okay, so this is like very comparable to Cassini or to the GW event, which is like a different motivation. But I mean, only from pulsars, the constraints are pretty strong. So bottom of line, it seems like the dark energies doesn't have like some hidden interaction, and then it's like even make like the problem of dark energy is like more strange. So this is like the bottom of line, I would say.
Thank you very much. The pizza is not here yet, so I guess we have plenty of time for questions. Jamie.
So do you have a sense of a floor to, I mean, how low do the constraints have to be before you abandon thinking about these kinds of extensions?
Oh, so I mean, the idea is also the following. I mean, also F of bar gravity, for instance, different theories of gravity, they could reformulate as chameleon type, as this like type of theories. Okay, so it's like, so what I'm trying to say, it's like a very general framework. It's not like to take, I don't know, Hordetsky, it's even simpler, but it's like equivalent to Galileans or F of R. Okay, so I mean, the idea is like, bottom of line, if you're using like different systems, you can actually test like many theories, even though you're testing like a particular model.
Is there some natural point? So let's say you get the constraint on beta down to, 10 to the -10. You then abandon that?
Yes.
why?
I mean, no, I mean,
What sets the natural lower limit?
I would say that, I mean, before we published like these papers, even like the solution weren't exist. So I wouldn't say that like now my motivation is like to continue to constrain these theories. But I mean, it's like to state that even the framework wasn't exist. So I mean, but it's pretty tight constraint. It's like, okay.
So you say you can already start thinking about Horndeski.
Can we move on then? They say, is that tight enough that we can stop thinking about these theories or no, we should just cite your papers.
I am in some sense, my statement is like very tight. It's very tight and it's going to be tighter. So.
But it sounds like that's then general. We can stop thinking about any of these theories. Is that right?
Yeah, but then you have like how the modification from where it's lambda coming from, why it has like this value, this all like
Well, you
questions.
still have the motivation to think about lambda, but it sounds like so far many of the solutions proposed are ruled out now.
Are ruled out, yes, that's correct. Yeah.
See, this is like,
Have ruled it out on.
this is a bit like f of r, where f of r was ruled out 10 years ago, but people keep putting it in and ruling it out more.
Yeah.
Just to show what they could rule out in principle,
Yes.
if it were still a theory.
So I mean, for f of r, for instance, I mean, many f of r theories, if you go like to the low energy limit, you get your Yokawa potential, right? And the Yokawa length is like related to the size of the system in some sense. If it's like in galaxies, it's like bigger than some systems. So this is like, I mean, you can predict more or less what is going to be like the future constraints on f of r or other theories. Here is like to state, I mean, this is like one from the novel ideas that the parameter, I mean, this formal coupling is actually related to NB over lambda. So f of r is like related eventually to some scale, some L. Okay? And here it's like related to the period. Okay? So this is like in the theoretical sense. The solution is depends on the period of the system. Okay? Barry?
A couple of questions.
Yeah.
First is, you're making all these tests in the flight problem. How is that different than just taking the theory, extracting out post-Newtonian parameters, and then comparing those from those things?
You describe the work in a very simple sentence, yes. I don't find a problem with this sentence. That's correct. But the post-Keplerian parameters, they are depends on the masses, but also now depends on modified gravity parameters. It's like generalized. That's all.
So in these systems, do the higher order post-Newtonian terms actually matter, or are you far enough away from the gravity?
That's an excellent question. So I mean, like in the sense that the double pulsar actually they introduced 2.5 post-Newtonian, 2.5, and it's going to be like higher in a few years, I guess. So and obviously, like in gravitational waves, usually you need like one or two, no more, unless if you're good like inside like the merger, which is like 4.5 or something like that, right? So, I mean, so what I'm trying to say is like these sort of like corrections that are like adding to the 2.5, to 2.5 like PN expansion.
And the last one is perhaps maybe a mean question. So let's say you do all this and you find out that data and lambda are completely inconsistent with GR. You found evidence for showing up here. What is the thing you point at before you say the GR is wrong? What's all the opposite things that are primarily going to be dominating these things?
Still, there are certain motivations for like modified gravity, maybe the Hubble tension, this sort of stuff, okay? But then it's like, okay, if still like in this system, GR is fully consistent, like increasing the question more.
I think that if it's not consistent, then what are you gonna do?
Oh, so then you can have like a Bayesian analysis, for instance, like to find statistically what is like the best theory, right? So it's one from the method that we have, like to test. So you have like one theory, auto theory. Let's put like in Bayesian statistic, and then like what is like the evidence for the best model.
You have a sense out of all these different tests, which of them are more robust with the astrophysics versus ones
Yeah.
where you have this quantum diagram, you could change how plasma processing.
Yes. Yes.
Which one, he's asking which one is the best, you think?
Oh, so far I think GR plus lambda. So
You know, which of the tests is most
oh.
independent of all these other.
Oh, I mean, pulsar, for instance, is like independent because I mean, bottom line, you get like these Planar parameters, measurements. It's one example. I mean, there are a lot, yes, but so I mean, the theory gives you like a relation between the parameter that you measure, omega dot, p dot, and so on, and you get like the relation to the masses, but also like to the modified gravity parameters. Now, in the original paper by Kramer, in the double pulsar, they tried like to do like the same thing for Teves, for instance. And then the curves actually like move away. I mean, they didn't match. So it was like ruling out the theory. Okay. Or in this case, it's going to be like really tight bound. Okay.
Now, what is it, only if you go back to the other slide you had it before, if you sort of a follow on from Ms. Forrest's question, the one with the constraints. You have you made a measurement, well, I was thinking of the one that was right at the end.
You repeat the
That
number?
one, yeah, so if you had a measurement that actually detected, let's say, in this diagram, some point in parameter space, how would that differ from, on a cosmological scales, from GR plus lambda?
On GR, on cosmological scales, I mean, needs to like to be solved.
Expansion and so on, right?
Yeah, yeah, that's correct. But I mean, because there you need also like that the scalar field would have like a behavior like of dark energy. So it's not going to be like the massless, right? So I mean, it's a bit like a different, I think. I would say.
Lambda like, but presumably it would make some finite predict. I mean, I guess what would the another way of turning it around and saying what are the existing cosmological constraints on that diagram? Because all the things you have
Oh.
there are
Okay, yeah, I
only close short length scale systems.
yes. From what I know, because this is like a huge literature, but there is like a certain paper by Mark Truden, okay, that also like introduced like in the conference last week. So he tried like to resolve the Hubble tension with the chameleon type theory. So I mean, it could give you like for certain potential and certain coupling of the chameleon, right? I mean, the scalar potential is like coupled to matter. You could resolve the Hubble tension in some sense.
I think beta, but if you know what is beta for that? It must be like 10% or something like that.
I think so. So there are like constraints, but not for the disformal coupling, not for the disformal. So it exists like with certain value. It's like, okay, here it's like solving the tension or something.
But I guess the idea is that you want these cannot be universal because the thing that's relevant for cosmology cannot be the one that's necessarily relevant for like pulsars. And this is related to, I think, what Neil was asking, that you really need some mechanism to kill all the cosmological things on a small scale, because otherwise, I mean, cosmology is much less constraining than like solar system or pulsars. So this chameleon or Weinstein or others, they make all of these very small on astrophysical scale. Yeah, but I think the lambda thing gets interesting because the cosmology, you don't have this energy scale. So I think you cannot really constrain this with cosmology. Okay. Lisa, I know you had the honest question there. Go ahead.
Very simple question. I love work on this. Thank you for the talk. We're one of the few on-site grads with perspective photos.
Okay, thank you.
You told me that my lack of that very well constrained and we well. Are those the only two options, or are there like other ways that energy can interact matter that we haven't filled out yet, or?
Oh. First of all, there's like a big ocean. Okay, so I mean, it depends like which, but I mean, this like spatial theories in some sense, because my host, she showed like some years ago that like other theories of gravity, they're like equivalent to these like two interactions. So this is like a pretty general framework. Especially for Densky and this sort of type, yeah, you can rewrite it as a chameleon type or as like a conformal and small interactions.
I think that we have right with that.
Yeah, if you have like a vector field inside, I guess it should be like different. Or if you have like other theories. Okay, so, but it's like a big ocean. So
Okay, so I think on that note, sorry, I interrupted you. Go ahead. I guess. If there are no more questions, now the pizza is here, so the timing was perfect.
yeah.
Okay, just thanks, David, again. We do have some online participants. If there are any questions, I think, yeah, Yanni and Tristan, I guess they're gone, so.
Okay.
I get,
Laughing, but no question.
yeah, no, very good. Yeah. Okay.